Hi guys, please like, share and subscribe, and contact this number if you want full lectures of any CM or CS subjects. Thank you.
Hi guys, let's continue our discussion on time series processes. So in the last video I had discussed with you the basics of a time series model, what it is exactly, and then we went on to discuss the autocorrelation function and the uh, autocovariance function. These are the two functions that we discussed in the last video. Okay, and then we discussed the conditions for stationarity. What is a weakly stationary time series? What is a strictly stationary time series, and all of that, right? So now let's move on and let's discuss like a bit more about stationarity. So when I have a stationary time series with me, whenever there is a stationary time series, these two rules are always applicable. Okay, the two rules are basically that the covariance gamma k, okay, covariance with a lag of k is the same as the covariance of with a lag of minus k. Okay, because k is a lag, its absolute value only matters, and the sign does not matter. Okay, because a difference of k and minus k is the same thing. Let's see how this works out. Okay, so what is a covariance with a lag of minus k? Okay, that will be the covariance between x t minus k, and it would be a covariance between xt and xt minus k, right? And a covariance with a lag of k will be the covariance between xt and xt plus k, right? This is what it exactly is. Now if you see these two are the same thing. How are they the same thing? If I write this as covariance of xt minus k and xt, right? This can be written exactly as this xt minus k and xt, the covariance between these two. I just interchange these two, and that I can easily do in the sense of covariance, because covariance is nothing but expectation of xt plus k comma into xt minus xt into expectation of xt plus k, right? This is what your covariance essentially is. That is the definition of your covariance function, right? So I can just interchange xt plus k and xt, right? Similarly here I can just exchange xt minus k and xt, right? So that does not matter, like I can change the order of these two. And now this t can be anytime. This t can be anytime. So if in place of t I just put t plus k, okay, let's just put t plus k in place of t, because t can be anytime. It can be any random time. So if t is like some different time, instead of t, if you have t plus k, then this becomes covariance of x. Now if in place of t I put t plus k, this becomes x t plus k minus k, which is the same as xt, and the second term just becomes x t plus k, right? So these two things, they are just the same, so I can just change the order of these two, and it does not matter, right? So see, gamma minus k is same as gamma k. Okay, these two are the same, it just depends on the lag, and lag can be on the right hand side or the left hand side. Similarly the covariance, similarly the correlation, autocorrelation is also the same, exactly the same thing. So how does that happen? This is just gamma k upon gamma 0. That's just your covariance upon the variance. Remember that variance can be written as gamma 0, because it's just the covariance of xt with xt with 0 lag, right? And this one can be written as gamma minus k upon gamma 0. So these two are the same thing, because these two covariants are the same. Okay. So the next thing is that throughout this chapter, you will notice these terms ET and ZT being used. Okay, they are used interchangeably. They mean the same thing. This is used to denote a white noise process. Now, if you have studied subject CM2 or subject CT8, you will know that a white noise process is nothing but randomness. This process is used to denote randomness. So basically, these are randomness in any system, randomness that cannot be predicted. So mostly what is done is that since these are errors or randomness, they can be assumed to be normally distributed. Okay, so ET is usually denoted with a normal distribution with a mean of 0 and a variance of sigma square. Okay, and the reason this is normally distributed is that when there is an error in a system, you would assume that that most of the errors are of a small deviation size. Okay, so this error, most of these errors would be small in magnitude. They can either be on the negative side or the positive side, but they will be small in magnitude. And then there will be outliers, which are very few errors would be very large. Okay, so that is how like most things in the real world function, and randomness is always assumed to have a normal distribution. So this is something that you'll have to remember. When I say that they are normally distributed random variables, they will be IIDs. They will always be independent and identically distributed. Okay, how that functions is, you have E0, E1, or you can write this as ET, ET plus 1, ET plus 2. Now these all will be IID random variables. Okay, which means that they are independent and all of them have the same distribution, which is normal 0 comma sigma square distribution. So all of their distribution is the same. They are identically distributed and they are independent of each other. They do not depend on each other. So the covariance between them, the covariance between any ET and any ET plus K, where K is not equal to 0. Okay, this covariance is always equal to 0. Okay, so this covariance between ET and ET plus K, when K is not equal to 0, okay, for any positive or negative lag, this will be 0. And the covariance between ET and ET, that is when this lag is equal to 0. Okay, these were all the cases where the lag was not equal to 0. So any lag, because they are IID, they do not affect each other, their covariance is 0. Their correlation is also 0. When I talk about the covariance of ET with ET, that's just the variance of ET. That is just the variance of ET. And variance of ET is, as we know, sigma square, which we have seen here. Okay, so that is how it functions, and this is how you need to this is what you need to remember about this random white noise, and this is also often denoted with the letter ZT. Okay, so the next thing we discuss are called as correlograms. What is a correlograms? This is a plot of the autocorrelation function against different lags. Now, what is the purpose of this? See, in real life, when we try to fit a particular process to a time series model, what is the first step? The first step is to check whether that process is a stationary time series or not. Okay. Uh, in order to check that, we draw correlograms. Okay, now what is the purpose of testing whether the series is stationary or not? If the series is stationary, we will eventually see that we can model a lot of stationary time series using the models which are suggested in this chapter. So stationarity is our prerequisite for modeling. We always need it. First thing, very important thing is that the process should be stationary. If it is not stationary, then what we will do is we will make it stationary, and then we will apply the models which are suggested further in this chapter. Okay. So now what do I mean by stationarity? Let's just recall that. Stationarity means that the expectation is same. That is, your process should have an overall average which is remaining constant. There should be no trend. Then the variability for individual values is the same. That is, the variance should be constant. And the third and the most important property is that the correlation or the covariance only depends on the lag. Okay, so your autocorrelation function or your autocovariance function only depends on the lag, and that is when I will call the series as stationary. So for this autocorrelation function to be only depending on the lag, I will have to check the autocorrelation of the data, which I will do by plotting it on a graph. So let's see what a correlogram looks like. So if you see this, this is a typical correlogram for a stationary process. Now what do you see? These are lags on the x-axis, and on the y-axis you have your autocorrelation function. Autocorrelation function can take a maximum value of 1 and a minimum value of -1, because correlation is between 1, -1 and 1, right? Now at a lag of 0, that is, how is the value related to itself? Okay. So at a lag of 0, your correlation will always be 1, because a value is completely related to itself. And mathematically, even if you think about it, it will just be a gamma 0, that is covariance between the value and itself with a lag of 0, divided by gamma 0, that is variance by variance, which is just 1. Okay. So we know that the correlation coefficient is just the covariance upon the variance. So it is the same as in the case where lag is 0, it's just gamma 0 by gamma 0, which is 1. So at a lag of 0, it will be 1. At a lag of 1, it will be a smaller value. Then at a lag of 2, it is getting even further smaller. Now why are they getting smaller and smaller? Because the process is purely indeterministic. That is, the relationship between further and further values reduces, right? Now if you see this process, it is a stationary process with a correlation or with a relationship existing up to lag 2. So your correlation basically for lag 1 is 0.5, for lag 2 is somewhat 0.25 if I see this, and further beyond that your correlation is just almost negligible. It's oscillating around the x-axis, which means sometimes it is negative, sometimes it is positive. Okay, but it is just randomness. These are that et terms that I was talking about. Okay, so this is just randomness. Like this can sometimes go negative, that previous value and next value has a negative correlation, or it can have a positive one. So this is just, you can consider it to be 0. This is negligible. Okay, up till here, up to the lag 2 it exists, beyond that it is negligible. Okay, and this series is a stationary series. Why can I say that? I can say that this series is stationary because the correlation only depends on the lag. For lag 0, it is 1. For lag 1, it is 0.5. For lag 2, it is 0.25 maybe. And beyond that, it is negligible. It is 0. Okay. So that is why, see, correlation can be said to depend only on the lag, and we can model it based on the lag, right? Now this is a correlogram. Now this is the actual data which is plotted here. They have given your actual data, and this is the what a stationary data usually looks like. It's just random data points plotted here and there. Okay, that is just a stationary. You don't see a basic trend here basically. But so now again consider the fact that this is not the correlogram. This is just the data plotted on a on a graph where you see your times. In the x-axis the times are given, not the lags, and on the y-axis you see your values, whatever values are taken. If you join these dots, you will observe that, see, what happens is you see some sort of a pattern here. Uh, the pattern is that uh, every value is somewhat related to its previous value, and there is no relationship further. Okay, maybe I observed this graph wrong here. Okay, if you see, they are considering that at lag 1 there is some relationship. Okay, but beyond lag 2 there is no relationship, right? So we were correct only. So let's see this. Okay, fine. So they've plotted this data. If you see this data, you will find out that up to 2 lags, okay, 1, 2 and 3, up to 3 values, see, they are somewhat around each other, and beyond that the value entirely changes. Okay, if you will see again, see, 1, 2, 3, 3 values are related, and beyond that it changes. 1, 2, 3, 3 values are related, and then it changes. So basic idea you can get from this graph is that every 3 subsequent values have some sort of relationship amongst themselves. That lag 0, lag 1 and lag 2 there is relationship, beyond that there is no relationship. Okay, so this is what a stationary process looks like, where there is a relationship up to 2 points, right? Next, this is one sort of a scenario where you have a stationary process. Next is not a stationary process. This is this is basically an alternating series. Now what do you see here? you see that the values are oscillating. Okay, the values are basically oscillating. That previous value is related to the next value. There is a, once there is an increase, then decrease, increase, decrease, increase, decrease. So there is a some sort of a negative relationship at a lag of, at all the odd lags there is a negative relationship, and at all the even lags there is a positive relationship, right? If you see this value, it's peaking, then falling, then peaking. So the next to next value is related to this value, right? But the next value is not. Next value is just inverse to this. Okay, so it increases one, decreases, increases, decreases. So wherever the lag is odd, the autocorrelation function is negative. Whenever the lag is even, the autocorrelation function is positive. So this is what you will see in the correlogram. See, here you see that your okay, this can also be considered as stationary to some extent. Why? Because your correlation is only dependent on your lag. Okay, so it is only dependent on your lag and it is oscillating. Okay, so with a lag of 0 it is 1, with a lag of 1 it is negative, then positive, then negative, positive, negative, positive, negative, so on and so forth, right? I told you at all the even lags you will find it to be positive, at all the odd lags you will find it to be negative, right? So that is how it functions, right? Okay, very easy to understand. Now what happens is the correlation is also reducing, okay, almost going towards zero after the ninth or the 10th lag. Okay, so this is because this process is purely indeterministic. The correlation keeps on reducing as the lag increases, right? So this is basically a stationary process as well. Now we'll see a non-stationary process. Now this is a series with a trend. A series with a trend cannot be stationary because if you see, if you think about it, if there is a trend, then your expectation will never be constant. Okay, there is an increasing trend here in the data, which means that your expectation would be increasing with time. Okay, for example, if I talk to you about the price of anything in the world, price of land, okay, it increases with inflation. So there is an inflationary trend, so you cannot predict the price of a land directly as a stationary random variable because it is increasing, right? So there is an increasing trend. You can see that. So here also increasing trend. Again, this process will not be stationary. So this will be shown by this correlogram. See, so there is no stationarity, and it is not also purely indeterministic. Okay, there is some sort of decay in the relationship, very low decay, but like it is not falling at all. And if you see, if you want to see this more clearly, if you want to see the decay somewhat, you can see it here. See, so what they have done is, yeah, they have taken a larger, they have taken a larger sort of data here, and they have tried to show you the autocorrelation function. So this is, there is some sort of lag, but it is never tending to, there is some sort of, you know, trend, and the autocorrelation is never going to zero. It is just falling and falling but never going to zero. So these are some things that you can observe. Okay, and then the next one is, if there is a seasonal trend, if there is a seasonal trend, what happens is your correlation function just oscillates. So if you'll see, if you think about the temperature in any year, okay, if you think about the temperature every June and December, okay, the temperature is just the opposite of each other. June very high, December very low. Okay, so if you see, at every 6 months, at a lag of every 6 months, there is a perfectly negative correlation, almost perfectly negative correlation. And if you see at a lag of 12 months, there will be a perfectly positive sort of a correlation. Why? Because if you see this year June, next year June, perfectly positive, then next year June, perfectly positive, then next year June, almost perfectly positive. So there is a seasonal variation. But if you will see this year June to next year this year December, 6 months, there is a perfectly negative correlation. Higher the heat, higher would be the cold. Okay, So that is how it works in general. Okay, so the idea is that this oscillates, this curve is oscillating, and that is what I mean by a seasonal trend. So you can look at your correlation functions and you can figure out like what is the trend in the data. And now if you have some oscillation, some trend, some increasing trend or some seasonal trend, if you have these sort of trends, you will try to make the data more and more stationary. How will we convert a non-stationary data into a stationary one? That is a discussion for the next chapter. Okay, for now we will get into the mathematics of time series. So the fair idea of correlograms was to introduce like what stationarity looks like on a correlogram and what non-stationarity looks like. Okay, so the next thing that I'm going to discuss is the problem with the autocorrelation function and the need for the partial autocorrelation function. So far we have discussed the autocorrelation function, which just measures the degree of relationship at different lags. Okay, so if there is xt and we are trying to measure the autocorrelation function, it will measure how xt is related to xt minus 1, xt minus 2, xt minus 3, so on and so forth. And it can be related up to infinite terms, but I will assume that it is related to past k terms. So this relationship between xt and xt minus 1 is denoted with a rho 1. That is a correlation at a lag of 1. Okay. Then next you can measure a correlation at a lag of 2, which will be rho 2. Then you can measure at a lag of 3, which will be just rho 3. And at a lag of k will be rho k. So how is it related to previous terms is what the autocorrelation function measures. But now there is a problem with this. The problem is that we know that xt minus 1 is related to xt minus 2. Okay, this is related to this term, right? So when I try to measure the relationship between xt and xt minus 2 using rho 2, okay, maybe there is no direct relationship between the two. Maybe the value of xt minus 2 does not influence xt. But what happens is xt minus 2 influences xt minus 1. That is, there is a relationship at a lag of 1, okay, but no relationship at a lag of 2, no direct relationship at a lag of 2. Okay, but what happens here is that since there is a relationship at a lag of 1, xt minus 2 will influence xt minus 1, which will in turn influence xt. Okay, so what happens is that if I try to measure the relationship between xt and xt minus 2, even though there is no real relationship, still this will give me some value. This will give me some value because xt minus 2 influences xt minus 1, which in turn influences xt. Okay, so there will be some positive relationship or negative relationship or whatever between xt and xt minus 2, even though there is no real relationship. So the problem we are facing here is that the relationship is transferred between terms, right? One term can influence another just because their intermediate term is related. Similarly, if I go for a larger lag, okay, maybe there is no real relationship between xt minus k and xt, but still my function rho k may take some positive value just because xt minus k influences xt minus k minus 1, and then which in turn somehow influences xt minus 3, which influences xt minus 2, which influences xt minus 1, and finally influences xt. Okay, so the problem is that the intermediate terms transfer the relationship from one term to another. So in order to eliminate this problem, the solution is the partial autocorrelation function, which is basically the relationship between xt and xt plus k given all the intermediate terms. If the value of all the intermediate terms is known, that is xt minus 1, xt minus 2, xt minus 3, if all of these are given going up till xt minus k plus 1, okay, if all of these values are given, then what is the relationship between the two, which is purely the relationship between this and not the relationship which is transferred through the intermediate terms. So how do I measure this? See, this is measured like xt, if it is related to its previous k terms, can be expressed in the form of partial autocorrelation functions. Okay, how xt can be expressed as, now this is the notation for the partial autocorrelation function. This is just a phi. Okay, phi 1, it is related with phi 1 as a factor phi 1 with xt minus 1. It is related with a factor phi 2 with xt minus 2. Okay, so on and so forth. It is related with phi k with a factor of xt minus k. Okay, so xt can be expressed as a linear equation of all its past terms. Of all its past terms, it can be expressed as a linear relationship, and then these past terms show what is the direct relationship between these individual terms and xt, right? So this is what a partial autocorrelation function is. It just shows the direct relationship and not the transferred relationship. Okay, that is the fair idea. I hope you got it. Okay, so now that is your partial autocorrelation function. How do we find it? We will try to find it by minimizing the mean squared error. Now, if you remember from subject CT3, a mean squared error is basically the square of the difference between the estimate and the estimator. Okay, this is the square of the difference between the actual value and the estimator. Now, this xt is your actual value. This is your actual value that you are trying to estimate using all of these values. You are trying to estimate using this estimator. So this is your estimator. And if you remember, your mean squared error used to be measured as MSE, was basically the actual value minus the estimator, that is theta minus theta hat squared, and the expectation of this. So mean squared error was the expectation of theta minus theta hat, where we used to do it in chapter number 10, point estimation. We used to take a difference between the actual value and the estimator, square it, and take the expectation of that. Similarly, here what we'll do, and we used to say that theta hat is the best estimator. The best estimator theta hat can be found when this error, this mean squared error, is minimum. We tried to minimize it because why? Because we want this theta hat to be as close as theta as possible. So we want this expected difference, the square of the expected difference between them, to be minimum. So we used to minimize it. Okay, and when we minimized it, we found a theta hat which was the best estimator. Similarly, here we'll try to find the best estimator by minimizing it. So what we'll do is we will try to minimize the MSE, the mean squared error, which in this case becomes the actual value minus the estimator. Estimator is phi 1 xt minus 1 plus phi 2 xt minus 2 plus so on and so forth up till phi k xt minus k. Now this function, okay, your mean squared error would be, let me write it here, MSE. Mean squared error is this. It is just the expectation of the actual value minus the estimator squared, and then I'm taking an expectation. So this term will be minimized using maxima and minima, which will in turn give me the mean squared error, which will in turn give me all of these estimates that are phi 1, phi 2, so on and so forth up till phi k. Now that's for your theoretical knowledge, that what are we exactly doing. How will we do it? This equation becomes a very complicated equation and cannot be fit using pen and paper. So this can be done on a computer. Okay, uh, you can calculate your partial autocorrelation function for any time series on R, which you will be doing in part B. But for part A, we will limit ourselves with two formulas which are given in table. Phi 1 can be calculated directly as rho 1. Okay, so the formula for phi 1 at all points of time will be that it is the same as rho 1, and phi 2 will be calculated using the formula for rho 2 minus rho 1 square upon 1 minus rho 1 square. This will be your formula for phi 2. Okay, so these are the formula that we'll be using for calculating the partial autocorrelation functions at lag 1 and lag 2, these two formulas are, they are given in the tables. I will tell you the page number in a bit. Okay, so these are given in the tables, and these formulas you will have to like apply directly. They can be estimated using R. You can find the partial autocorrelation function of any series, which you will learn in part B. But for part A, you just need to be concerned with partial autocorrelation function at lag 1 and lag 2. Okay.